Last class we were doing operations on complex numbers, and I think under operations we had started with the process of division, right? Did we basically complete the geometrical interpretation of division? Can anybody confirm that? Did we learn how to locate Z1 by Z2 on the Argand plane? If no, we can start with that. Okay, so we did not do that. Fine. All right. So last class we just did Z1 by Z2, the quotient of complex numbers Z1 divided by Z2. So how do we basically represent this operation or this particular result on the Argand plane, right? Let's try to understand the process. Meanwhile, all of you have understood that when you write Z1 and Z2 in the polar form, that means when you write Z1 as R1 cos theta 1 plus I sin theta 1, and you write R2 as R2 times cos theta 2 plus I sin theta 2, right? And here we know these are called the polar forms. Okay. Now, when you do this operation Z1 by Z2, what does it become? It becomes R1 divided by R2. Can somebody complete it? R1 divided by R2. Yes. What should I write? Cos of? Right. Theta 1 minus theta 2 plus I sin theta 1 minus theta 2. Absolutely right. Okay. So this is what we had learned, and we had also quickly drawn two conclusions out of it. And what were the conclusions? The conclusion is that the modulus of the quotient is quotient of their moduli. So this was the first conclusion that we had drawn, looking at this part. So as you can all see here, this is the modulus. This is the modulus of Z1 by Z2. And these angles that you see here, they are arguments of the complex number, correct? Yes or no? Right. So this was our first conclusion. Second conclusion was that the argument of Z1 by Z2 is argument of Z1 minus argument of Z2, which is directly coming from this particular fact. Is it fine? Any questions? Any concerns? Now, talking about the geometrical representation of Z1 by Z2. So where is Z1 divided by Z2 lying on the Argand plane? Okay. So keeping this in mind, let us say this is my Argand plane. Okay, so in the Argand plane, let us locate Z1 first. Let this be Z1. In fact, since I'm doing Z1 divided by Z2, I'll locate Z1 slightly up. Let's say somewhere over here. Okay. And let's say Z2, I'll represent over here. Okay, so this is Z1 and this is Z2. Okay. Now, where is Z1 divided by Z2 located on this Argand plane? Let's try to figure that out first. Now here, this length is R1. Let's name it R1. This angle is theta 1. Let's name it theta 1. Okay. This length, let me write theta 1 slightly up. Yeah. This length is R2. Okay. And this angle here is theta 2. Now, I have to locate such a point on this Argand plane, which is at a distance of R1 divided by R2. And which is at an angle of or at an argument of theta1 minus theta2. Correct? So let's say this entire thing is theta1. This yellow angle that you see is entire thing is theta1, right? Now let me drop from here by theta2 angle. So I'm just reducing it by theta2 angle. And on that particular angle, I'm making this blue line. Okay. I don't want to make it very long. Just sufficient enough to accommodate R1 divided by R2. Okay. Now R1 divided by R2. Let us take that length on our compass. Okay. So let's say we have a compass with us. We take R1 divided by R2 length on that compass. And from O, we cut that arc over here. Okay. So this length, I'm just erasing the other part. This length that you see represents R1 divided by R2. I'll write it down over here. R1 divided by R2. Okay. So this point that you see here, everyone, this point is your Z1 divided by Z2 point. Z1 divided by Z2 point. Okay. Now, a very interesting thing that you would notice here is that if you connect a triangle, okay, let me ask this as a question to you. Let's see how many of you are able to answer this. If I connect Z1 to this point, okay, let's say I name it as point A, I name this as point B, and I name this point to be point C. Okay. So I get a triangle over here. Okay, and now what I do is, let me take a different color here, maybe a gray color. Let me connect Z2 to some point on the real Z axis. Let's call this point to be, point P. Okay, something comma 0. Let's call it as A comma 0. Okay. And I ask you this simple question. Find A if triangle OAC is similar to triangle OBP. Okay, so treat this as a question from my side. Let's see how many of you are able to answer this. You have to find this A coordinate of this point P, or you can say the real part of this complex number P, such that triangle OAC is similar to triangle OBP. Can you solve this one and give me the response? Anybody? Okay. See, all of you, please pay attention. OA by OC will be equal to OB by OP, because these two triangles are similar, so their sides are proportional. So OA is what? Let me write them down first of all in terms of expression. Okay. This is because the triangles are similar and hence sides are proportional. Correct now? So OA is what? OA is R1. OC is what? R1 divided by R2. Yes or no? Because we already know this length, R1 divided by R2. See, I've written it in blue color over here. Correct? What is OB? OB is R2. Correct? And OP is something which is of length A. So this length is, as of now, length A. Correct? Now, when you simplify this, what do you end up getting? First of all, this R2 will go on top. Okay, and R1 and R1 will get cancelled off. And there's an R2 on the right side also. This also will get cancelled off. So what's your A value? A value will be 1, right? So this point that you see, it's actually 1, 0. Maybe let me write it below this. So this point that you see is actually 1, 0. So this question was actually asked in one of the competitive exams where they had made this triangle, and they also mentioned that A is Z1, B is Z2, C is Z1 divided by Z2. Find the coordinates of P such that these two triangles are similar triangles. Okay. So this actually was a question asked in a competitive exam. Okay. So geometrically speaking, if you want to construct Z1 divided by Z2, you first make a triangle using O, B, and P, right? Make a triangle similar to it over here by using O, A, and some unknown point C. That C will actually become Z1 divided by Z2. I'll repeat this process again. If you want to make, or if you want to locate the Z1 divided by Z2 point on the Argand plane, first make OBP, because B will be known to you. P anyways is 1, 0, so you can easily plot it on the real Z axis. Make a triangle OAC similar to OBP, and you will realize then that your point C, because O is anyways known, A is anyways known, so that C point that you will be anyways getting when you are making the triangle similar to OBP, that C point will be the Z1 divided by Z2 point. Is it fine? Any questions here? Any questions, any concerns, anybody? Okay, let's take a simple question. If you have copied this down, let's take a simple question. Can you move to the left, this part? Aditya? Right, this part? So in the last class, we had derived these two results, but I'm just quickly recapping it for you so that you are fresh with that particular fact. Let's start with the problem. Let's start with the question. Yeah. First, we'll take a simple question here just to revise our basics operation. So this question says, if x minus 3 by 3 plus I plus y minus 3 by 3 minus I is I, find the value of x and y. Find the value of x and y. X and y are real values. Yes, any success? Anybody? Try out, don't worry about right or wrong. Just give your best. Yes, Akit. Giving you some time, not to worry. Okay, let's start the discussion. I think as of now, nobody has solved it. So let me just write down these expressions. Slightly spaced apart because I want to do some operations on it. Okay, so as of now, this is the expression given to us, right? Now, what do we do here? We multiply and divide each side of the numerator and denominator with the conjugate of the denominator. So conjugate of 3 plus I is 3 minus I. So we multiply 3 minus I in the numerator and denominator both. Okay. And let's do the same operation here as well. Okay. Now take this as a hint. Proceed further. Yes, still no response. Okay, let's do this. So this will be x minus 3, 3 minus I. 3 plus I, 3 minus I. Please remember the property that we had discussed, that z into conjugate of z is mod z square. Correct? So z into conjugate of z will be mod z square. That means it will become under root of 3 square plus 1 square square. So under root and square will get cancelled off. So you'll get 9 plus 1, which is 10. Correct? Now, what will happen here? This will become y minus 3 by 3 plus I divided by 10 again. Take the 10 to the other side. If you take the 10 to the other side, what does it become? This will be equal to 10i. Yes or no? Right. Now, what do you do here? Separate the real part and the imaginary part on the left side. So how will you get real part? Real part will be obtained when x minus 3 multiplies with 3 and y minus 3 multiplies with 3. Correct? So the real part that you will obtain on the left hand side will be 3 times x minus 3 and 3 times y minus 3. Correct? The imaginary part, what will you obtain? Imaginary part will be obtained when minus 3 multiplies with, when minus I multiplies with x minus 3 and I multiplies with y minus 3. So when minus I multiplies with x minus 3, you will get 3 minus x. And when I multiplies with y minus 3, you will get I times y minus 3. So I'm taking I common already out, so don't need to worry about I. Okay. Now on simplification, this gives you 3 times x plus y minus 6 as the real part, and imaginary part will be y minus x. Okay. Now even this 10i, I will write it as 0 plus 10i. Now remember, when you are comparing two complex numbers, you compare their real parts and imaginary parts on both sides, on both LHS and RHS, right? So on the comparing real with real, you get 3 times x plus y minus 6 as 0, which clearly means that x plus y is equal to 6. And when you compare the imaginary part, you get minus x plus y, or you can say y minus x, both are same, is equal to 10. Now, using this equation and this equation, let's solve for x and y. Now, very simple. If you add them, what do you get? Just add these two expressions. What do you get? 2y. 2y is equal to 16. So y value is 8. Correct? Simple. Now put this in 1. So x plus 8 is equal to 6. So x value is minus 2. Right? Saket, slight mistake in your answer, but well tried. At least you answered. Nobody else answered this question. So x is minus 2 and y is 8. Is it fine? Any question, any concerns here? Do let me know. Any questions, any concerns? Do let me know.
So please could you scroll up a little bit?
Yes, sure. Is this fine enough, or you want me to scroll?
Yeah, it's a little low also is fine.
Yeah. Let me know once you're done so that we can move on. Done? I think it was Zain, right? Zain? Sorry, Zian. Zian, are you done?
Yes, sir. Thank you so much.
Okay. All right. So with this, we are going to go towards our logarithmic operations on complex numbers. But before that, I would like people to have a bit of idea about the Euler's form little bit more. Okay, because Euler's form is going to be very, very handy when we are trying to find out the logarithm of complex numbers. In fact, it has got a lot of other importance as well. So we'll be looking into Euler's form slightly more closely now. So as I already told you that Euler basically proved that cos theta, just a quick recall of this concept, cos theta can actually be written as e to the power I theta. Okay. So this was actually one of the major proofs in the field of mathematics, which was done by Euler. And that too when he was partially blind. He was having cataract this time, and despite that, it was no deterrence for him to prove this. Okay. And because of this, you can actually represent the polar form, which is r cos theta plus I sin theta, also as r e to the power I theta. Okay. So we all know that this form of a complex number is called the polar form. And this form of the complex number, sorry about that, L became too fat. Yeah. This is polar form. And this is what we call as the Euler's form, right? Okay. So in Euler form, if you have understood this, I have a very small question for you all. Find modulus of e to the power I theta plus 1. That's first question. Argument of e theta e to the power I theta plus 1. That's my second question. Third is argument of e to the power I theta minus 1. And fourth question is argument of e to the power I theta minus 1. Okay. So if you have understood the Euler's form, can you just figure out what is the modulus and the argument of primarily these two complex numbers, e to the power I theta plus 1 and e to the power I theta minus 1. Why I'm giving this as a question is because this result itself, you need to keep in mind, because many a times direct questions are asked, pertinent to these two complex numbers. So that time, instead of you wasting your time figuring it out, what's their argument and what's the modulus, let's do this exercise right now itself. Yes. So just give your response by putting the appropriate question number next to it. Else I will not know which one you're answering. Let's have around 2 minutes for this. Okay, so let's take this up. I think many of you are still solving it. It's very simple. If I take e to the power I theta, I've already written that it is cos theta plus I sin theta, right? Now, the moment you add a 1 to it, okay, so we already know this result. Now we add a 1 to it, it will become 1 plus cos theta plus I sin theta, right? Now I have clubbed 1 with cos theta because both are real. And if you recall your half angle identities, 1 plus cos theta can actually be written as 2 cos square theta by 2, isn't it? So this is from your formula. Recall this formula. Cos of 2a is 2 cos square a minus 1, isn't it? So if you take a 1 on the left side, you will end up getting 1 plus cos 2a as 2 cos square a. Correct? So this becomes 2 cos square theta by 2. And we can also break sine theta as 2 sine theta by 2 cos theta by 2. Correct? Take 2 cos theta by 2 common. When I do that, I end up getting cos theta by 2 plus I sin theta by 2. Yes or no? Any questions here? Now, if you compare this with your r cis theta or cos theta plus I sin theta, this becomes your modulus. Correct? And this angle theta by 2 becomes your, argument. Yes or no? Correct. See what I'm doing. You just compare this. With r times cos theta plus I sin theta. So your r will become 2 cos theta by 2. And theta itself, let me not write theta here, let me write phi here because else it's not right to say theta is theta by 2. Yeah, so let's call it as phi. So phi is your theta by 2. Okay, so the answer to the first part is the modulus of e to the power I theta plus 1 is 2 cos theta by 2. Remember this result because many times it is helpful. Argument is theta by 2. Argument is theta by 2. Clear? Any questions? Now, does this give you a hint how to proceed with the third and the fourth part? So I would request you guys to give it a try because it gives me more happiness when it comes from your side. When you solve it, it gives me more happiness because then I feel my hard work has paid off. Yeah, do the third part, everyone. So I'm waiting for your response. Done? Okay, now see. Again, e to the power I theta minus 1, I can write it as cos theta minus 1 plus I sin theta, right? So I just have to subtract a 1 from this expression that I've already written on the top. Now, recall this formula that you had already done in your trigonometry that cos of 2a is 1 minus 2 sine square a, isn't it? So that means cos of 2a minus 1 is negative 2 sine square a, right? Can I use that over here and write this as negative 2 sine square theta by 2? Yes or no? And Sine theta, I can break it up as 2 sine theta by 2 cos theta by 2. Any questions so far? Now, if I take 2 sine theta by 2 common along with an I, okay, along with an I, what do I get? I get cos theta by 2. Now, mind you, -1 is like I square. Okay, this -1 that you see here, this -1 can also be treated like I square, isn't it? So when you take an I common from there, it becomes I sine theta by 2. But mind you, everybody please pay attention. You cannot say that 2I sine theta by 2 is your R or your modulus, because modulus is always a real number, right? So what I'm going to do is I'm going to do a little step, a little bit more, extra here. I'm going to write this I as cos pi by 2 plus I sine pi by 2. Okay. Now we already know this fact that when two complex numbers are multiplied, their arguments get added up and their moduli get multiplied, right? So this has already a modulus of 1. Okay, so 1 and this will get multiplied, so it will become 2 sine theta by 2, and arguments will get added up. So your arguments will become pi by 2 plus theta by 2 and I sine pi by 2 plus theta by 2. I hope you all remember the property of complex number multiplication, that when two complex numbers get multiplied, their moduli gets multiplied and their argument get added up. And their arguments get added up, right? So having written it like this, now we have a solid conclusion in front of us that this will become our modulus. Okay, let me write it below it. This will become your modulus. And these angles that you see here, these are of course same angle and they have to be the argument of that complex number. Okay, so this becomes 2 sine theta by 2 and argument here is pi by 2 plus theta by 2. Clear, everyone? Now this expression that I have written, this also is very important expression, so I would request you to note it down, because many times that expression also is helpful in solving few questions. Is it fine? Any questions, anybody? I hope everybody knows that I can be written as cos pi by 2 plus I sine pi by 2. This is the polar form for I. Of course, you can write a 1 here also, but doesn't make a difference. 1 multiplied to anything is the same thing. Okay, so if this is fine, time for another question. Let's take another question. Can I move to the next slide if you're done? Anybody still copying it? Oh, Saket is still copying it. Fine, it's fine. I'll wait. Scroll up to this position. Is this fine, Saket? Okay, let's move on to a question. Let's take this concept. Yeah, it's given that mod of z minus 1 is 1. Z is a point on the Argand plane. Show that. Now this is given as a show that question, but it is very easy to objectify such questions also. show that z minus 2 upon z is I tan argument z. Yes, any success, anybody? See, let's say I have been given a complex number z minus 1 and it has been told that its its modulus is 1. Okay. So here z minus 1 is some complex number and we know its modulus at least. Okay. Now let's say the argument of z minus 1 is theta. Or you can say 2 theta, whatever you want to call it. It's up to you. Okay. Now, if argument of z minus 1 is theta, then since you know its modulus and its argument, how do you write that as a Euler form? How do you write z minus 1 then? You'll say simple, sir. Modulus e to the power I argument. This is how you write it as a Euler form, isn't it? So this is the Euler form representation for z minus 1. In short, you're trying to say z minus 1 is e to the power I theta. Right? Yes or no? That means z is 1 plus e to the power I theta or e to the power I theta plus 1. Right? Now, knowing this from the previous slide is actually helpful. Now, since we know this, we can write this as 2 cos theta by 2 into cos theta by 2 plus I sin theta by 2. Okay. So this is something which we have already done in the previous slide. So I'll just write it here. See the previous slide. Okay. In case you're referring to your note little later on, and then you're wondering how did I write it like this, then you can always go to the previous slide and check it out. Right. Now, if this is z, what is z minus 2? Because I need a z minus 2 in the expression also, right? So I need a z that I've already got. I need a z minus 2 also. So what is z minus 2? You'll say e to the power I theta minus 1. Correct? And this expression we have just now seen in the previous slide that it was 2i cos theta sine theta by 2 times this. Okay, this also see the previous slide. Correct? Okay. Now, as per our given expression, we have to find or we have to prove that z1 z minus 2 by z is I tan argument of z, right? So let us write down our left hand side. So whatever we want to prove, the left hand side I have to write the value of that. So z minus 2 is e to the power I theta minus 1 by e to the power I theta plus 1. And let's write down their values in the polar form or whatever I have written on top of it, like this. Okay, so 2i sine theta by 2 times cos theta plus I sine theta by 2, I have written it. And denominator is 2 cos theta by 2 times cos theta by 2 plus I sine theta by 2, right? Now these two will straight away get cancelled. 2 will also get cancelled. So what I'll be left with? I'll be left with I tan theta by 2. Okay. Now is theta by 2 my argument of z? Let's check it out here. So my z was this, and in the previous slides I discussed that this is the modulus and theta by 2 is the argument. These two angles are the argument, right? So yes, from here I can easily conclude that the argument of z was theta by 2. So this theta by 2 that you see over here, I can replace that with argument of z. And that is my RHS. That is what I wanted to show. Nice. Hence shown. Is it fine? Any questions here? Any questions in this particular solution? So knowing the result for these two, knowing the results for this guy and this guy was really, really helpful. So people who know the result, they probably save a minute or two in solving the question. And those who don't, they spend around a minute or two to get it. But remember, even a minute saved is basically an extra question solved.
So could you explain how argument of z became theta by 2 here?
Okay, so how did this become theta by 2? Let's go to the previous slides. Yeah. Oh, sorry. I'm sorry. This was the slide. Yeah. This question. Second part. Isn't this z for me in my next?
Right. Yeah, we had got it. Okay.
So because of this result, and in fact, I have written it on that slide as well. So this is the modulus. If you compare it with r cos phi I sin phi, that means if you compare this with the polar form, then your 2 cos theta by 2 is the modulus and theta by 2 is the argument. So hence argument of z here is, this is my z, which is this expression, will be theta by 2. Is it fine? Okay.
Yes.
Now we were actually doing an operation here which was logarithms. Okay, logarithms of complex numbers or use of logarithm on complex numbers. So whenever you are trying to use a logarithm on a complex number, the best form to represent your complex number would be the Euler's form. Okay, so the Euler form is one of the you can say easy to handle forms when it comes to applying logarithmic properties on complex numbers. Now, instead of teaching you anything, you already know logarithms, so there's nothing to teach in logarithm. But yes, we'll take a question. Let's say I have a number I to the power I. Okay, I have this complex number I to the power I. Okay, let's find out log to the base e of this complex number and whatever we get, let's find out sine of that angle. Okay, let's find out this. Let's take this as a question to begin with. Okay, now let me solve it, because that will give you an idea about how to proceed. So whichever complex number you are raising it to some power, that complex number you write it in the Euler's form. So how do you write the Euler's form for I? Of course, we have just now did it. 1 e to the power I pi by 2, isn't it? This is the Euler form representation for I. Anybody who has who is not very sure about it, other than I believe Advait would not be knowing it. Advait, are you comfortable with complex numbers? Have you done that before?
I've done the very basics. I mean, I'm not sure, but I'll catch up.
Okay. Yeah, of course, this is the last class of complex numbers, so things have already taken a shape to the difficult side. Yes, I to the power I can be written as 1 e to the power I pi by 2, because 1 is the modulus of I and pi by 2 is the argument of I, correct? Now, if I raise this to the power of I itself, so let me write we know here. Yeah. So I to the power I will be what? By the way, 1 e to the power I pi by 2 is just e to the power I pi by 2. You need not write that one. Now you're raising this to a power of I. So as per the exponent laws, what will happen? The powers will get multiplied, isn't it? So I pi by 2 multiplied with I will give you what? I square pi by 2. Right? And I square is -1. So that becomes e to the power negative pi by 2. Yes or no? Now here is a surprising element. The surprising element is that, and many of you would be surprised, that I to the power I is actually a purely real number. Yes. Many people are taken aback by this information. Oh, I to the power I thought it would be terribly imaginary. But no, I to the power I is actually a purely real number. Okay. And its value is e to the power negative pi by 2. Anyways, let's move ahead with the question. The question is asking me to find sine of log of I to the power I. So let's find out log of I to the power I to the base e. So for that, I to the power I will replace with e to the power minus pi by 2. Okay. How was that calculated? How was that calculated means I showed everything on your screen right now. You want me to show you what is the value of e to the power minus pi by 2? Is that what you want me to show, Krishnendu? Because if you're asking how was that calculated, it is right on your screen. Okay, those who haven't learned logarithms, maybe because you missed out the bridge course session. Okay, so just let me show you on Learnist which module to watch. So all of you have signed up on this platform, Learnist platform, which is our LMS platform, other than Advait, I believe. Okay, so in that, those who have joined in late, you can go to, one second. Yeah. Yeah, you can go to Maths JEE Mathematics 2022 and graph and its transformation, the third lecture. If you see the third lecture, in fact, you can, yeah, third lecture and second lecture also partially. Yeah, second lecture I've started explaining logarithmic functions. Okay, so second and third you need to watch out. Okay, so already my recordings of logarithms are there. Okay, so today itself after the class, please watch these recordings. Okay, all right, meanwhile focus on whatever is going on. How is the power I was calculated? How is it calculated? Like how I'm showing you. I was e to the power I pi by 2. I raised it to the power I. So this got raised to the power I. I into I became I square. This became -1. So this is the value. The way to calculate itself is what I am showing on the screen. No? If you ask its value, then I have to pick up a calculator. Okay, let's calculate its value also. Let me just do this operation. E to the power of minus pi by 2. Yeah. Its value is roughly 0.207-ish. Okay. If that is the question, then answer is negative 0.207. Anyways, coming back to the question. So this, as per the log properties, this power will come in the front. So this will become minus pi by 2 log e to the base e. Okay. Log e to the base e is actually a 1. So this will become a minus pi by 2. Okay. Now, if you take sine of log e to the power, or you can say log I to the power I to the base e, what are you actually doing? You're actually taking sine of negative pi by 2. What is sine of negative pi by 2? Write down this answer on the chat box, everybody. Sine minus pi by 2. Quickly. -1. Absolutely right. Okay. So this becomes your answer to this question. Okay. So basically what I wanted to show you that was the Euler form was very instrumental in solving this question. Clear, everybody? Okay, so if you are fine with this question, actually it was a very easy question to solve. We can now take up problem where you will require Euler form, and of course log will also be required. So let's take that question. We will be doing limits and derivatives next, Zan. So today, after complex numbers, we'll start with limits and derivatives. Now, many people want to ask me why limits and derivatives, because see, limits and derivatives is a gateway for you towards complex number, towards calculus. Okay. So the earlier you start, the better it is, because you'll get more time to practice your basic, calculus part. All right. So here we have this question. 1 plus I to the power minus I. Express this as a plus ib. So the question is asking you to write this as a plus ib, and of course you have to write a value and b value as well while you are doing it. So indirectly you have to find your a and b as well. Try it out, everyone. Okay, I can understand this question may be slightly difficult for you to solve, but is anybody trying it out at least? Okay, Arthur is trying, Pratik is okay, fine, fine. So, so it makes sense for me to give you some time. Okay, please do it. Please try it. Trying is more important than anything. Getting the answer is, of course, secondary here. So when you try, your gray cells grow. You start applying your concepts. At least you get to know what works and what doesn't work. Okay, somebody wants to give me the first. Okay, so if I were to solve this problem, I will first write down the Euler form representation for 1 plus I, right? So what is the modulus of 1 plus I? Root 2. Argument of 1 plus I, pi by 4, right? So at least in Euler form, I can write 1 plus I as root 2 e to the power I pi by 4, correct? Now I'm raising it to the power minus I, means I'm raising this to the power of minus I. Okay. Break it up like this. Mind you, you'll end up getting minus I square here. So this will give you this. So what is I square? I square is minus 1 again. So minus minus will become plus. Now, is this hint good enough, or do you want me to go further in solving the problem? Okay, good enough. Fine. Then I'll stop here for 1 minute. Take it forward to the extent you can. I am always there to help you out after that. See, what I did here was, Shreya, you already know 1 plus I modulus is root 2. Its argument is pi by 4. So in the Euler form, I wrote 1 plus I like this. So this is the Euler's form. Correct? Now I raise it to power of minus I, means you're raising this whole thing to the power minus I. Now exponent properties, I hope you are aware that you can split this power separately on these terms like this. So root 2 separate, e to the power I pi by 4 separate, and both have the power of minus I minus I. All right, so this becomes root 2 to the power minus I, e to the power I pi by 4. Now I'm sure many people are stuck. What to do with this guy? Correct? Okay, never mind. I'll show you what to do with that guy. See, root 2. In fact, let me take you to the logarithmic properties. Any number k can be written as e to the power ln k. Right? This property, if you recall, this was actually the fundamental logarithmic property. This property is actually called the fundamental logarithmic property. Fundamental logarithmic property. So e to the power ln something is the same something, right? How does it come? Very simple. Let's say if I call ln k, or better called as log k to the base e. So ln is ln is basically log to the base e. If I call this as x, it means k is e to the power x by log definition. Correct? People who have not studied log before, you'll have to watch the video before you understand this. Okay. And what is x? X itself is ln k. Hence this property. So what I'm going to do here is this root 2, can I write it as e to the power ln root 2? Right? By the very same logic, root 2, I'm writing it as e to the power ln root 2. Correct? Which means e to the power minus ln root 2 into e to the power pi by 4. E to the power minus I ln root 2 e to the power pi by 4. which further can be written as e to the power pi by 4 into e to the power I ln 1 by root 2, because the minus will go and sit as a power on root 2. So root 2 to the power minus 1 becomes 1 upon root 2. Now compare this to r e to the power I 5. So who is acting like r? Who is acting like r? Right, e to the power pi by 4 is acting like r. Correct. Who is acting like 5? ln 1 by root 2. Correct. Now, the question setter had actually asked me to write it as a plus ib form. But since you have already written it in polar form, Euler form, you can always write it in the polar form also, right? That is, you can always write it like this also. In other words, your a becomes r cos phi. This is your a. And what's your b? B is r sin phi. So this becomes your capital A of the question. This becomes your capital B. So comparing it with the point form, we can say that my A will be R. R is what? E to the power pi by 4. Cos phi. Cos phi is what? ln 1 by root 2. Okay. Similarly, B will be what? E to the power pi by 4 sin ln 1 by root 2. Clear? So this implies 1 plus I to the power minus I can be expressed as A plus I B. Is it fine? Any questions, any concerns? This is your final answer. So what was the trick to solving this question? The two steps here, they were trick to solving this question. One, you knowing that you have to write it in the Euler form. If you are not aware of it, then many people will start applying so many other things which is not going to be helpful. And the second trick here was knowing how to write root 2 as e to the power ln root 2. That was another trick. Clear? All good so far? Any questions? Any questions, any concerns? So I'll scroll it down to the last. If you want to copy anything, most of the part is here. Pratik, you were there when I did log properties? No? See, if you write log of m to the power n, doesn't it become n log m to the base b? So let's say if I had minus 1 log root 2, what will happen? As per the same logic, this will become root 2 to the power minus 1. And what is root 2 to the power minus 1? 1 by root 2. Dear all, you have to practice logarithms to the extent that you are not surprised by these properties. I'm not saying that you have to do PhD in logarithms, but at least do it to the extent where you can handle these simple tools of logarithms. Any questions? Any questions, any concerns? Okay. So with this, we now move on to square roots of complex numbers. So we have already done operations like comparison, addition, subtraction, multiplication, division. Now we did logarithm. So now we should also learn how to square root or how to find the square roots of a given complex number. Let's take that. So with your permission, can I move on to the next slide? Sure. Okay. Now let's talk about square roots of complex numbers. Square roots of complex numbers. Square root of any complex number, let's say if I take any complex number a plus I by, that is also a complex number. Okay, but here I will get two answers for it. Okay, and they will both be complex numbers only. Now, this is something very different in real valued function. When we were talking about root x as a real valued function, what we learned that root of x will only give you one answer, right? Let's say root of 4. If I put x as 4, I'll only get one answer for it, which is 2, right? The positive answer, of course. So we used to call that as the principal root. But that restriction is not anymore applicable when you are applying the same concept to complex number, because we are no longer restricted ourselves to real valued function. Okay. So when you are finding the square root of any complex numbers, you'll get two complex numbers as your roots. If you're taking cube roots of complex number, you'll get 3 answers. If you take fourth roots of complex number, you'll get 4 answers, and so on and so forth. So that is how basically we apply the square rooting of complex numbers. So let us find out what are these 2 answers. But I would like to take this question with the help of an example so that you understand the process better. Let's take an example to find out the square root of a complex number. Let's say I want to find out the square roots of 5 minus 12i. So all of you please pay attention. All of you please pay attention. I'll be helping you to find the square roots of 5 minus 12i. So let us say I take the square root of this complex number to be, let me write it like this, to be plus, sorry, p plus iq. Okay. Now, many people say, sir, you said 2 answers will be there. Why you have assumed it to be only 1? So if there are 2 answers, I need not assume it to be multiple answers. In fact, P itself will take 2 values and Q itself will take 2 values. Okay. So I don't have to write it as, let's say, P1 plus IQ1 and P2 plus IQ2, because P will automatically end up taking 2 values and Q will also end up taking 2 values. We'll see how. Okay. So let under root of 5 minus 12i be P plus IQ. Okay. Now square both sides. Square both sides. So when you square both sides, you end up getting this. Okay. Let's write down the expansion of P plus IQ. So this will give you P square. IQ square will be minus Q square because I square itself is minus 1. And you'll end up getting 2PIQ, which is I times 2PQ. Okay, so I have written real and imaginary separately so that we can now compare the left hand side and the right hand side. Oh, by the way, so far so good. Any concerns here, anybody? So we are basically looking out for the value of P and Q. And in light of that, I am doing this operation. Okay. All right. So if you compare the real part and the imaginary part on LHS and RHS, let's see what do we get on LHS and RHS. So on comparing the real part, what we'll get P square minus Q square is 5. Correct? And we end up getting 2PQ as minus 12. Okay. Let me call it as expression number 1 and let me call this as expression number 2. So from 1 and 2, we need to solve for P and Q. Right? We need to solve for P and Q. Okay, so solve for P and Q. Now, for solving for P and Q, there are two approaches. Okay, approach 1 and there's an approach 2 also. Let me take one approach at a time. So first approach is, many people, they write, so I'll just write down the expression once again. Yeah, so from the second expression 2PQ equal to 12, you can write your Q as, sorry, minus 12. You can write your Q as minus 6 by P, okay? And put this in this expression, correct? So if you put it in that expression, you get P square minus Q square. Q square will be 36 by P square equal to 5. That is to say, P to the power 4 minus 5P square minus 36 equal to 0. And if you just factorize this, this will be broken as 9P square plus 4P square. Take P square common and this is going to be, yeah, this is going to be factorized. So it will give you P square plus 4 times P square minus 9 equal to 0. Correct? So this cannot be 0 ever because P is a real number, square of real number is greater than equal to 0. And if you add a 4, it will be greater than equal to 4. So this guy can never be 0. That means if the product of these two is 0, that means P square minus 9 only can be 0. Correct? So that means P square is 9. So P value will be plus minus 3. Yes or no? Any questions? Any questions? Any concerns? Okay. If P is plus 3, okay, let me write it here. If P is plus 3, what is Q value then? Look at this equation. If P is plus 3, what is Q value then? Minus 2, correct? And if P is minus 3, then what is Q value then? Plus 2. Okay. So what does this imply? This implies that your P plus IQ can take two values, which is 3 minus 2i and minus 3 plus 2i. So these are your answers for this given question. So these are your square roots of your complex number. Clear? Any question, any concern here? Anybody has any doubt in this? Kindly highlight. And note it down because I'm now going to move on to the next method. Please repeat why P square plus 4 cannot be 0. Why can it be 0? I would like to know from you first. If you justify it can be 0, I will also justify it cannot be 0. Tell. Why do you think P square plus 4 can be 0? Because the answer that you will give, that will help me to understand whether you have actually understood what a complex number is. Yes, Anika, I'm waiting for your answer. Why do you think P square plus 4 can be 0? Is this possible? This can only be possible when P is here plus minus 2i, isn't it? But when you write a complex number, is your P and Q themselves imaginary? No, they are both real. So if you're writing a complex number as P plus IQ, your P and Q are real like numbers and their squares can never be negative. Okay. All right. Now coming to the second approach. So I'll do my second approach here. I'll have to make a long arrow here. Second approach. Now this is the approach which even I like using it. Yeah, so let me explain you the second method. So in second method, what do we do is, we already know that p square minus q square is 5, right? And 2pq is minus 12, right? Most of you would have done this formula in your basic, I would say class 10th maybe. Have you all done this formula? X plus y the whole square is x minus y the whole square plus 4xy. Have you all done this formula? Okay. In this formula, put your x as p square and put your y as q square. Okay. So can I say p square plus q square whole square can be written as p square minus q square square plus 4p square q square, which is like writing this. Yes or no? Yes or no? Okay. Now, can I say that p square plus q square whole square will be square of p square minus q square, which is 5 square, and square of 2pq, which is minus 12 square. By the way, we all know that they form the Pythagorean triplet 5, 12, and 13. So from here, can I say p square plus q square whole square is 13 square, which only leaves us with only 13 as the value of p square plus q square, correct? Yes or no? Is it fine? Okay, so now why not minus 13? Why p square plus q square is only 13? Why not minus 13? Can it be minus? Can the sum of the squares of two real numbers be ever be negative? No. So that is why it is only plus 13, not minus 13. Right? Now, using this and using this, let us solve for p and q. So p square minus q square is 5, p square plus q square is 13. Just add them, you get 2p square as 18. That means p square is 9. That means p is plus minus 3. Just subtract them. You get 2q square as 8. That means q square is 4. That means q value is plus minus 2. Okay. Now, understand here that you are getting two values of p and two values of q. So when you are writing p plus iq, how many combinations of p plus iq will be possible? 4 combinations, right? So if you take a plus plus of both, you get one combination. If you take minus and plus, another combination. You take plus and minus, another combination. You take minus minus, you get another combination. So basically what you realize is that in this approach, this is giving you 4 answers. One is 3 plus 2i. Other is minus 3 plus 2i. Another is 3 minus 2i. And the other one is minus 3 minus 2i. But What we had discussed a little while ago was that we are only going to get 2 answers. But right now I see there are 4 answers coming up, right? So which of the 2 answers will be accepted and which of the 2 answers will be rejected? Any idea, anybody? And why? That's very important question. 2 answers will be accepted, 2 answers will be rejected. Which 2 will be rejected and why? Second and third is accepted. Okay. So why is first and fourth rejected? Okay. The answer to that is hidden in this expression. See, this expression says PQ value should be -6. So in which of them P into Q? P into Q is -6. Is 3 into 2 -6? No. So this is rejected. Is -3 into 2 -6? Yes. So it will be accepted. Is 3 into -2 6? 3 into -2 -6? Yes. So that will also be accepted. And is -3 into -2 plus 6? No. So this will be rejected, right? So only the second and the third is going to be your answer. So under root of 5 minus 12i is, you can write it in one go, 3 minus 2i, and just put a plus minus outside. That will automatically take care of both the answers. Is this okay? Is this understood? Any questions, anybody? Okay. Now, there is a set of questions that I would like you to do here. But first, please copy down the second approach. There's a third approach also, which is actually knowing the formula. But before giving you the formula, I thought I would make you do some hard work, because formula should not be taken for granted. Formula is not the end goal of our learning, right? It is just a tool that is helping us to solve a question. Okay. So note this down, and then we will take few questions. In fact, one question, and then I'll give you a formula. Copied, everyone? Okay, so let's take a question. You can use any of the two approaches. It's not binding that you have to use the second approach or the first approach. Any approach you feel like, you can take that up. Okay, let's take this. I would like you to solve the third one here. Just the third one. Okay, there are 4 questions here. Just solve the third one. That's more than enough. Other questions you can take down them as your assignment, as your homework. Just put your response on the chat box. Now, in the previous method, I was just explaining you the process, hence I was taking so much time, but I think you can jump directly now to the result quickly. See, let's say you're assuming this to be P plus IQ. Okay. So a few steps you can directly write. You don't have to explain everything in word by word. So on squaring both sides, what do you get? Minus this is equal to P square minus Q square plus I times 2PQ. Correct? So compare this with minus 8 and compare 2PQ with minus 15. Okay. Now you already know that P square plus Q square is what? Under root of A square, 8 square plus 15 square. Now remember 8, 15 and 17 are Pythagorean triplets. 8, 15 and 17 are Pythagorean triplets. So you can directly write this. Now when you add it, you get this as 9. That means P square is equal to plus minus 3 by root 2. Sorry, P is equal to plus minus 3 by root 2. I've already taken care of the root. Okay. And if you subtract it, you get 2Q square is equal to 25. So Q is equal to plus minus 5 by root 2. Correct. So 4 answers are possible, but you are only going to write the ones where the product of PQ is minus 15 by 2. So you will end up getting only 2 combination. One is C root 2 minus I 5 by root 2. Another will be minus 3 by root 2 plus I times 5 by root 2. So these are your answers to this question. Right? So you don't have to explain everything while solving this as a question, for your JEE exam. Now, many of you would like to know a formula. That is there any formula to find the square root pretty fast? Yes, there is a formula. Formula for under root of P plus IQ. Okay. So the formula is under root of, you can say plus minus under root of mod of this complex number. Whatever complex number is P plus IQ, let's say I call this as a complex number Z. Okay. So mod of that complex number, we all know how to find mod, right? Plus real part of that complex number. So add the real part of the complex number to mod of that complex number divided by 2. Now, the answer will be plus here under root of mod Z minus real part of Z by 2. If your Q value is negative. So if your Q is negative here, this number is negative, then this would be your, sorry, if this is positive, other way around, sorry. Yeah, if this is positive, then this will be a plus sign here. So if Q is a positive number, you will put a plus sign here. And your answer would be this. Everything will remain the same. Mod Z plus real part of Z by 2 minus I under root of mod Z minus real part of Z by 2 if your Q is negative. If your Q is negative. Okay. I'll just show a quick demonstration of this. Let's say I want to find out the same complex number, minus 5, minus 8, minus 59. So my Z here is minus 8 minus 59. Now this is your Q. Correct? This is your Q. So Q is negative. Which formula will I follow? The second one, because this is only applicable when Q is negative. So your answer will be plus minus under root of mod of this number, mod of this complex number will be 17 plus real part of Z. Real part of Z is minus 8 divided by 2 minus I under root of mod of complex number, which is 17 again, minus real. Minus means minus 8 by 2. Okay. So this will easily give you the answer as 3 by root 2 minus I 5 by root 2. The same answer that we had got while solving it in a lengthy way. Okay. So this you can collectively write it as plus minus 3 by root 2 minus I 5 by root 2. Now it is up to you. You want to remember this formula and solve it. And let's say if you forget it, then God bless you. Or you want to follow the approach and solve it. It is completely up to you. Okay. So using this formula, can you do second one? Find out a square root of minus 5 plus 12y. Use this formula so that you have hands-on on your formula as well. Is it done? Okay, so which of the two formula will be applicable here? What is my Q value here? Positive or negative? What is Q value here? Positive or negative? Positive, right? So I'll use the first formula. So your square root will be plus minus, okay? Now, under root of mod z is 13, plus real part is minus 5 by 2, plus I under root of 13 plus 5 by 2. Okay, what does it give you? Plus minus? Acha, 8 by 2 is 4, root 4 is 2, and 18 by 2 is 9, root 9 is 3. So it will be plus minus, you may write I after 3 also, plus minus 2 plus 3. This is your answer. Can a trig function be defined on a complex plane? Yes, why not? All your rules of trigonometry is applied to complex plane also. Why not? You can find cos of a complex number also. I don't know whether you have learned Osborne rule. Have you done Osborne rule? Hey, you are an AP guy, no? You must be knowing. Pranav Baingam Padi. Yeah. So you can apply complex numbers. You can apply trigonometry on complex numbers also. Okay. So with this, we are now moving on to a very, very important theorem, because some of you would have this question in your mind that, sir, we only learned square root. But what about other powers? How will I raise a complex number to some rational power? Right? Of course, we are not talking about irrational powers here. So is there any rule by which we can basically learn how to find any complex number raised to a rational power? So yes, there is a theorem, right? That theorem is called the de Moivre's theorem. The de Moivre's theorem. Okay, so this theorem is going to be helpful in raising any complex number to a rational power. Okay, where P and Q are integers, right? So this is basically a rational quantity, a rational number, a rational power, you can say. Yes, Pranav. It is basically taught along with hyperbolic trig functions. Okay. Acha, not this one. Some people would be confused that what is this hyperbolic trig function. We will discuss it when the right time comes. Yeah, anyways. So when you are raising a complex number to a rational power, there is a theorem. Of course, we are not going to prove this theorem. Okay, that is beyond your scope. So there is a theorem called de Moivre's theorem. This is a French name. Okay, it's not de Moivre. Many people call it as Moivre. It's Moivre, de Moivre's theorem. Okay. So first of all, I'll be talking about two situations when this P by Q is actually an integer. Okay. So this is our first case that I'll be discussing. Then I'll be discussing when P by Q is actually not an integer. So because P by Q, P may be, let's say 5 and Q may be 1, right? So that means it becomes an integer. Positive, negative doesn't matter. Okay. So case number 1 is when my P by Q is actually an integer. So in such case, de Moivre's theorem says that if you have a complex number which you have written in the polar form like this, and you are raising the complex number z to the power of n being an integer here, then what happens is that the modulus gets raised to the power of n and the argument get multiplied by n. Right? So what happens? The modulus gets raised to the power of n and the argument gets multiplied by n. Understood? Now many people would say that it is very easy to perceive this from Euler's form. Yes, if you write it from the Euler's perspective, if you raise it to the power of n, that means you are raising this also to the power n, which means it becomes r to the power n e to the power I n theta. So if you write it in the polar form, it becomes this. Okay. Another way of perceiving it is, you are actually multiplying this complex number to itself n number of times. Correct? And when you are multiplying complex numbers, the moduli starts getting multiplied with each other, but arguments start getting added to each other. That's another way to perceive this result. Correct? Could you spell the theorem's name? De Moivre. De Moivre theorem. Advait, do you know French? Have you learned French in school? Okay. Now, why I'm so particular about the pronunciation is because, let's say, if you become an international student, let's say, students like Pranav who are planning to go abroad. So if you go abroad and you are sitting with, the foreign students, you should know how to pronounce properly, right? Else full Maryadi will go, no? Okay. Now see, this is very important and some important pointers to be noted. Okay, some important pointers to be noted. De Moivre's theorem cannot be applied to such cases where, number one, if your complex number is written like this. Okay. So let's say this is an imposter. This is, let's say, a term which tries to mimic a polar form, but it is actually not a polar form. So here, if you apply z to the power n, it cannot be written like this. So please do not misapply or wrongly apply your de Moivre's theorem on this. Okay. Why I categorically took this as an example is because in the past, your seniors have done this mistake. Right? So please do not do this mistake because this is not in the polar form. Not in the polar form. Okay. If you actually want to apply it to it, then you have to convert it like this. R cos pi by 2 minus theta plus I sin pi by 2 minus theta. And then apply the power of n. But in that case, it will become r to the power n cos n times this. So it is n pi by 2 minus n theta plus I sin n pi by 2 minus n theta. Okay, this is fine, but this is not fine. Okay. Yes, Raj, exactly. That is what I was discussing. Okay. Now, other mistake people do it is sometimes again, there's another Chinese mall, another Chinese product here. Some people will give you questions like this. Okay. So here they will put a cos and a sine, but these two angles will be different. These two angles will be different. Okay. Here also note down, you cannot write it like this. This is not acceptable. So please make a note of this, very, very important. So be aware of these two imposters. Clear? Okay. Now, let's take a problem on this before we move on to the case number 2. So this is our first case where your power is plain and simple an integer. Whether positive, negative, doesn't matter. This theorem will be applicable for any n which is an integer. Okay. All right. One more thing I would like to give you before giving a question. If you reciprocate, I think it's a special result of this, but still I'll make a mention of it so that everybody is fine. If you reciprocate cos theta plus I sin theta, what does it mean? It means you're raising cos theta plus I sin theta to the power of -1, correct? So what does it actually become? It actually becomes cos of, now this power will get multiplied to the argument. So it will become 1 into theta plus I sin -1 into theta. On expanding it, this becomes cos minus theta plus I sin minus theta. And we already know that cos of minus theta is as good as cos theta, and sine of minus theta is minus sine theta. So you can also write 1 by cos theta plus I sin theta to be cos theta minus I sin theta also. This result I am giving you separately because this is very commonly used. Okay. And the generalization of this is, so in general you can say that if you have cos theta plus I sin theta raised to the power of, sorry, there's a minus here. Yeah. If you have a raised to the power of n, it can actually follow the de Moivre's theorem. Okay. So here de Moivre's theorem will be applied, but not to the first two cases, right? Because writing this is as good as writing this. Correct? In fact, let me write it like this. Correct? And writing this inside form is as good as writing cos theta plus I sin theta to the power of -1. So -1 and outside there is an n. So they will both get multiplied and become cos theta plus I sin theta to the power of -n. Okay. So that becomes cos of minus n theta is as good as n theta. And sine of minus n theta is minus sine n theta, right? That is what we have done. Okay, so please remember this. This is a very, very commonly seen expression. Hence, I am making a special note of it for you all. So note this down. Right. So basically for cos theta plus I sin theta, the conjugate is the reciprocal. Exactly. Shall we take a question now? If you have copied this down, time to take a question.
So could you go back to the last part just for a minute?
Oh, yes. Why not? Why not? Third part, this entire part, right?
So no, just the last part, the white part.
Just right. Okay. In the white part, you just note this down. This is very important. This part. Oh, it's not coming in my box. Yes, Adit. Let Zayan copy and then I'll take you to the yellow part of it.
Done.
Yeah. Let me know once all of you are done copying it so that we can take up a question. Okay, great. Let's take a question on the first case of de Moivre's theorem. Yeah, let's take this question. Express cos theta plus I sin theta to the power 4 whole divided by sin theta plus I cos theta to the power 5 in A plus IB form. Give me a response as A value is this, B value is this on the chat box. Okay, so put the expression for A and B and let me know the result. Correct. The denominator is a imposter form, right? So be aware. Yes, anybody? See, just look at the denominator term because that is what is bothering us. Numerator term is fit and fine. Numerator term is very similar to whatever we have done. So if you take this term, which is cos theta plus, sin theta plus I cos theta to the power of 5. Okay. What I'm going to do is I'm going to break the base part here as I take I common, and you have cos theta minus I sin theta, right? So if you open the brackets, it becomes I to the power 5 cos theta. Acha, by the way, you can write this as correct, because cos theta minus I sin theta is reciprocal of cos theta plus I sin theta. So minus power can be clubbed with 5. Okay. And I to the power 5 is just an I. I to the power 5 is just an I. Okay. So your denominator finally simplifies to this expression. Now put it back. So your given expression, let's call this expression to be E. So your given expression E can be now written as cos theta plus I sin theta to the power of 4 upon I times cos theta plus I sin theta to the power minus 5. Correct? Now 1 upon I is minus I. 1 upon I is minus I. This powers can be written as a single power of cos theta plus I sin theta, which is power of 9 now, because 4 minus 5 will become a 9. Now, if I apply the de Moivre's theorem on this, this is how it is going to look like. Correct? Now, opening the bracket, it will become minus I square. Minus I square is plus 1. So it becomes sin 9 theta. Correct? And minus I cos 9 theta. Correct me if I am missing out anything. Do let me if I am missing out anything. Okay. So your A value and B value are now pretty obvious. Your A value is sin 9 theta, B value is minus cos 9 theta. So this becomes your answer to this question. Clear? Any questions? Any questions? Any concerns?
So could you explain that part? So I to the power of 5 cos theta plus I sin theta to the power minus 5.
See, this term is what? This term inside here is cos theta plus I sin theta to the power minus 1, no? And you're raising whole thing to the power of 5. Makes sense? This term, Zayan, is nothing but this term, no?
Yeah.
So what I did was, I individually gave the power of 5 to I also and power of 5 to this guy also. So I to the power 5 became, and this became cos theta plus I sin theta to the power minus 1 into 5. What is minus 1 into 5? Minus 5.
Yeah. Because it's the reciprocal.
After that, you know what happened. Yeah.
Yes.
Any questions here? Any questions here? Anybody? Okay. Now we'll move on to case number 2. But before that, we will take a small break because it's already 7 o'clock. I'm sure most of you will be feeling hungry. So case 2 will be slightly longer. So I wanted to take a break here. So we'll take a small break. Right now it's 7:04. We'll meet at 7:19. Exactly 15 minutes from now. After a 15 minutes break, we'll discuss the case 2 of de Moivre's theorem. Okay. Enjoy your break. I'll see you in 15 minutes time. During the break, we normally are logged in only. We don't log out. So this is just for Advait. So just keep logging here. I will also be I'll be switching off my camera and my mic. Now we are going to take case number 2 when your P by Q is not an integer. That means it is actually of the form P by Q, where P by Q cannot be expressed like an integer. For example, let's say 3 by 4, or let's say 1 by 2 itself, right? Or 1 by 3, right? So how does de Moivre's theorem react to this situation? Okay, now before I make you understand how de Moivre's theorem changes for this situation, I would like to ask you this simple basic question, that when you raise any number to a power of P by Q, let's say when I raise 2 to the power of, I'm just taking an example here, 2 to the power of 3 by 5. What are you actually doing? And how many answers do you expect from it? Let's say you allow your answers to be in the complex domain also. What are you actually doing here? So this means you are actually raising 2 to the power of 3 and taking the fifth root of it. So if you want to write it as a fifth root, so it will be looking like this, fifth root. Okay. So when you're taking a fifth root of 8, okay, 8 being, let's say, any complex number also, how many answers do you expect from it? Square roots, you got 2 answers. Cube root, 3 answers. The fifth root, how many answers do you expect from it? Right. It's going to give you 5 answers, right? So now we are going to learn the same even for any complex number. Okay. So when I raise a complex number to the power of P by Q, let's say I have a complex number. In the polar form, it is expressed like this. Okay. And when I raise this complex number to the power of P by Q, what actually I'm doing, I'm raising it to the power of P. And then this I'm raising it to the power of 1 by Q, means I'm taking the qth root. So how many answers do I expect from this? How many answers should come out from this operation? Right. Q answers will come out from it. Now let's see how de Moivre's theorem helps us to find those Q answers, right? So I'll be giving you ready-made result. In fact, I'll be deriving it with you. Not the derivation, but just the outcome of what de Moivre's theorem actually works in such cases. So let's say if I raise this to the power of P, I end up getting r to the power P cos P theta plus I sin P theta, right? Right? Now what do I do? Or what does de Moivre's theorem say after this? So de Moivre's theorem says that write this cos P theta as cos 2k pi plus P theta at both these positions, at sine position also, at cos position also. Okay, like this. Okay, so I'm still doing this part. Mind you, I'm just doing z to the power P part. So in z to the power P, I follow the de Moivre's theorem, which I've already studied before going for the break. But a small change I made to this expression. I basically changed my P theta with 2k pi plus P theta. Right? Here also I change it with 2k pi plus P theta. Now what is the benefit of doing it? What is the benefit of doing this? The benefit of doing this is first of all, the expression doesn't change. Right? The expression doesn't change. But I will end up getting my Q answers adjusted here. We'll see how. Now, when you raise this to the power of Q or 1 by Q, let me write it like this. Yeah. So basically, what are you doing? You're raising this to the power of 1 by Q. So again, apply the de Moivre's theorem that you had learned in the case 1. That means you raise that power 1 by Q on your r to the power P and multiply 1 by Q to this expression. Okay. Like this. Right? Now, why does it happen? The proof for that you will not be given right now because that's not a part of your scope here. But let's see the use of this expression. So once you have got this, De Moivre's said that to get your Q roots, you start putting your K value as 0, 1, 2 till Q minus 1. Okay. So when you start putting your K value as 0, 1, 2 till Q minus 1, in this expression, let me call this expression as expression 1, then that starts giving you your Q different answers. That means you start getting your Q answers that we had speculated over here. Okay, note this down because I'm now going to show you a demonstration for it. A small demonstration. And by the way, this term that you see, this term has to be a real term, okay? Because it is a modulus, right? Modulus has to be real. You cannot accept imaginary answers here, okay? All right, let's take a quick example of it. Let us say I want to find out I to the power of 1/4, okay, or 3/4, let's say, just to right. So I is a complex number here which is acting like the z in our case, and I want it to be raised to the power of 3/4. By the way, if I raise I to the power 3/4, how many answers are we going to expect from this operation? Anybody? Right, we are going to get 4 answers, right? Because essentially it is I cube to the power of 1/4, which is 4th root of I cube, right? So 4th root means 4 answers should be coming. Exactly. Now let's see De Moivre's theorem. How does it help us with this? So first of all, I itself, I can write it as 1 cos pi/2 plus I sin pi/2. Okay. So first raise it to the power of 3, or you can directly jump to the result also, but I'm doing it slowly. So when you raise it to the power 3, 1 cube will become a 1 only, and 3 will get multiplied to pi/2. Correct? Correct? So I cube is this. Now, when I raise this to the power of 1/4, before that, what did I say? Before that, even before we do raising it to the power 1/4, rewrite this expression like this. 1, instead of cos 3 pi/2, write 2k pi plus 3 pi/2. Now here understand that even if you write your 3 pi/2 as 2k pi plus 3 pi/2, it doesn't make any difference to our expression because sine and cos both are periodic with a period of 2 pi. Correct? Both are periodic with a period of 2 pi. Isn't it? And because of that, there is no change in the expression that you have written. There is no change in the expression you have written because cos theta and cos 2k pi plus theta are same thing. Sin theta and sin 2k pi plus theta is same thing. Okay. Now here I'll raise it to the power 1/4. So 1 to the power 1/4, that is 1 itself. And that 1/4 I'm going to multiply to this argument. So this divided by 4. So basically I have reached which step? I have reached this step. This step. Okay. Now, in order to get my 4 answers, I have to put k value as 0, 1, 2, and 3. In fact, this is something which many books also don't tell. Your k could be any 4 consecutive integers. You can start from anywhere. You can start with 5, 6, 7, 8. You can start with 100, 101, 102, 103. But now these ones are the ones which are very easy to manage. Hence, in books also they say put k value as 0, 1, 2, and 3. Okay. Or put 4 consecutive or put q consecutive values starting from 0. But in reality, you can put any q consecutive integers that you want. Your answers are not going to change. Achha, what will happen if I put, instead of, let's say here we are supposed to put k as 0, 1, 2, 3, right? What if I put 4 also? What will happen? Any guesses? Any guesses? If I go beyond 3, what will happen? Anybody? If you put beyond 4, your roots are going to repeat. So if I put a 4, it will give me same value as what I got for 0. If I put a 5, I'll get same value as what I get for 1. If I put 6, I'll get same value as what I got for 2. If I put 7, I'll get same value as what I got for 3. If I put 8, I'll get again same value as what I got for 0. Right? So that is the reason why we don't put anything beyond 4 consecutive values, because our roots will start getting repeated. Okay. So we'll see. We'll see in this example itself. Okay, now let's start putting the value. When you put k as 0, what do I get? What do I get when I put 0 in this expression? You get what? You get cos 3 pi by 8 plus I sine 3 pi by 8. So this is one of the answers. If you put k value as 1, what do you end up getting? Cos, tell me, 2 pi plus 3 pi by 2, which is going to be 7 pi by 2. You're going to get 7 pi by 8 plus I sine 7 pi by 8. Is it fine? Is it fine? If I put k value as 2, check for yourself. You will end up getting cos 11 pi by 8 plus I sine 11 pi by 8. Unnecessary bracket here, so I'll just remove it. Yeah, it erased more than I expected. Is it fine? Any questions? Any questions so far? If I put k value as 3, what do I get? What do I get? I'll get cos. I'll get cos 15 pi by 8 plus I sine 15 pi by 8. Clear? Any questions? Any questions? Any concerns? So these are your 4 values of your answer. This, and this. Okay, by the way, here if you notice, after this my arguments have overflown. That means it has gone beyond pi. So if you want, it is up to you. If you want, you can write it as cos. This can be written as 11 pi by 8 can be written as minus 5 pi by 8. Absolutely right. So you can also write it like this. No issues. You'll end up getting the same answer. Okay. Here also you can write this as cos. Let me write it in white. Yeah. Here also you can write it as cos minus pi by 8 plus I sine pi by 8. Okay. Mind you, I had actually crossed that minus pi to pi interval of your argument. So principal argument normally is between minus pi to pi. We all know that. So in these cases, you may also write it like this. Okay. Understood how de Moivre's theorem works? Any questions? Any questions? Any concerns? Okay. So now I'll give you a question from my side. But anything you would like to ask or copy or note down, please do it right now. So one question that is coming from one of you is, sir, can I use this for square root as well? Yes, of course, you can use this for square root. Because square root is also covered under the very same approach. Because 1 by 2 is also a p by q power, isn't it? Okay. Let's discuss a question. And to this question, actually, I wanted to cover a topic also, which is called cube roots of unity. Cube roots of unity. Unity means the number 1, correct? Cube roots of unity. So now I would request everybody to give me what are the cube roots of the number 1. So what are the 3 answers that we get for this? Please do this and let me know your results on the chat box. I'm giving you around 2 minutes for it. I don't have to repeat the question, my dear Zayan. It's already written on the board. I want cube roots of 1. Well, 1 is one of the answers, Arthur. Okay, so if you want me, I can write 1. But what are the other 2? Now you are into the complex plane. You can give your answers which are even complex. So earlier we used to restrict ourselves only to one value because we were learning real valued functions whose output and input both should be real. But now your output, input, anything that you want to put into the function and anything that you are getting from the function, they can be non-real. No, Advait, but good try. See, let's do this process. Now, 1 as a complex number in polar form can be written as 1 cos 0 plus I sin 0, right? So can I now write this as 1 cos 2k pi plus 0? By the way, you need not write plus 0, it is just 2k pi only. But just to rhyme with the approach that we had taken. And now when you're raising it to the power of 1/3, you can raise this to the power 1/3. And remember, here only real answer will come, which is actually a 1. And you multiply 1/3 with your 2k pi. Okay. Now, here start putting your k value as 0, 1, and 2 because we are finding the third root. So we have to stop till 3 minus 1, which is 2. So 0, 1, and 2. Okay. So what happens when you put k as 0? Yes, the answer is not going to change because of that. You can try it out, Pratik. Yeah. So when you put k as a 0, what happens? It becomes 1. By the way, 1 to the power 1/3, it is as good as a 1. So, let's not worry too much about this guy. So it will be cos 0 plus I sin 0, which is actually a 1 itself. That's our very first answer that I wrote here. Okay. I think Arthur told that answer. Now, when you put k as a 1, what do you end up getting? You end up getting cos. Let me write it in yellow. When you put k value as 1, what do you end up getting? You end up getting cos 2 pi by 3 plus I sin 2 pi by 3. Correct? Cos 2 pi by 3 is minus half. I sin 2 pi by 3 is root 3 by 2. So basically it becomes minus half plus I root 3 pi by 2. This complex number is commonly called omega. Commonly called means it's not like every time you see an omega, that means it is minus half plus I root 3 by 2. No, not like that. Normally we call it as omega, but omega could be used as a Greek symbol to represent any other thing also. Okay. And if you put k as a 2, you end up getting cos 4 pi by 3 plus I sin 4 pi by 3. Okay. If you want, you can also restrict your arguments to principal arguments. So 4 pi by 3 is as good as minus 2 pi by 3. So you can write your answer like this also. On simplification, this will give you minus half minus I root 3 pi by 2. Minus half minus I root 3 by 2. This is actually called the square of omega. Now, people are surprised when they see this. So actually, is this the square of this omega? Yes, it is. How? I'll show you. Look at this expression and look at this expression. What do you see? What do you see in their arguments? So if I do this operation, what will happen? As per de Moivre's theorem, this 2 will go and multiply with the argument, isn't it? So won't it become cos 4 pi by 3 plus I sin 4 pi by 3? And that is what is the square of the omega. So this term is actually omega. This term is actually omega. So square of this will be omega square. Got it? So completing the result over here, one of them is definitely 1 Arthur, but the other two, which was not known to you till today, is minus half plus I root 3 by 2. And this is commonly known as omega. We call it omega. And minus half minus I root 3 by 2, which is actually known as the square of the omega. Okay, I know some question will be running in your mind, but we will answer those questions in some time. But first, copy this down, everybody. Make a note of this. Copied? Okay. Now, a few important things about cube root of unity. Pranav, we are doing case 2 of de Moivre's theorem. And in that, we have already covered the case 2. We have already taken cube roots of unity. And now we are taking some important properties of cube roots of unity. Okay. Never mind, it has been recorded, so you can always watch the recording. Okay, pay attention. The first property is, if you see omega and omega square, okay, any power which is a multiple of 3, if you raise in on any one of them, that means if I raise this to the power of 3k, or if I raise this to the power of 3k, the result will always be a 1. The result will always be a 1, right? Because it's very obvious, because it is as good as saying omega cube to the power of k. And omega cube is what? Since omega is a root of cube root of unity, omega cube is 1. Correct? So this is 1. So you are raising 1 to the power of k actually, right? And that's nothing but it's going to give you a 1 only. So I'm just writing these two, and this is going to be a 1. Same here also. The second one will give you omega to the power 6 to the power k, which is anyways 1 or 1 square, you can call it. That will be 1 itself. Is it fine? Any questions? Second important result is omega value is minus half plus I root 3 by 2. And omega square value is minus half minus I root 3 by 2. Can I say that they are conjugates of each other? Yes or no? Right? So note this down, that they are not only squares of one another. Let's say omega square is a square of omega, but omega square is also a conjugate of omega. Okay. And now something very interesting. Since omega cube is equal to 1, I can write omega cube as omega into omega square, which means omega square is 1 by omega also, right? So write this down also, that not only omega square is the square of omega, it is also the conjugate of omega and is also the reciprocal of omega. Okay. So note these down. These are very, very important aspects. Where can we use this? So many places, a lot of questions you will be getting. Don't worry. So we'll be using there. Just a second. Okay, next property. Next property. The sum of the three cube roots of unity will actually be 0. This is one of the most important properties which will be useful in problem solving in other chapters also. How? The proof is very easy. We already know omega value is minus half plus I root 3 by 2. And omega square value is minus half minus I root 3 by 2. Correct? So if you see your LHS, you can write omega and omega square values that we have already seen in the previous slide. Now negative root 3 by 2 plus root 3 by 2 will cancel each other. 1 will get cancelled with minus half, giving you a 0 as the answer. Okay. Note this down. Very, very important property. Done. Now, an extension of this property is, if you raise the cube roots of unity to a power of p, okay, then this result will be 0 if p is not a multiple of 3. And this result will be 3. Sorry, this result will be 3 if p is a multiple of 3. Okay, let's prove this. Let's prove this property. But for proving this property, How many of you are aware of this formula? AQ minus B cube is A minus B, A square plus AB plus B square. All of you are aware of this formula? Oh, right. This is one of the identities that you have learned in junior classes also. Okay, good. Okay. So what I'm going to do is I'm going to write 1 cube minus omega cube. Okay. In fact, I'm going to write a very interesting thing here. 1 to the power p cube minus omega to the power p cube. Okay. So in light of this expansion, can I write this as 1 to the power p, which is 1 only, minus omega to the power p, okay, into 1 square, which is 1, or you can write, if you want, you can write it as 1 to the power p also, doesn't make a difference. Okay. And what about this? This will become 1 into omega to the power p, and this will become omega square to the power p, which you can write omega to the power 2 whole to the power of p. Okay. So from here, what I can do is I can write 1 plus, or 1 to the power p. If you want, you can write 1 to the power p. 1 to the power p plus omega to the power p plus omega square to the power p as this expression 1 minus to the power this to the power 3 divided by 1 minus omega to the power p. Correct? Yes or no? So this LHS can be written like this. So I'm basically writing the proof for this. Yes or no? Now understand here. If P is not a multiple of 3, then what will happen? This term 1 minus omega to the power p will not be 0. That means this guy will not be 0, because it will be 0 only when p is a multiple of 3 as per our very first property, as per this property, omega to the power k or omega to some power p, which is a multiple of 3, that will only give me 1. So this is not going to give me 1 minus 1, hence it is not going to give me a 0. But what will happen to the numerator? If you see, omega to the power p cube is as good as saying omega cube to the power p, which is actually 1 to the power p, which is 1. So this numerator will actually become what? This numerator will actually become 1 minus 1, and denominator will be a non-zero quantity. Sorry for writing 0 there. Yeah. And this will be a non-zero quantity, any non-zero quantity. So overall your answer is 0 by non-zero, which will actually give you a 0. That's your this expression 0 that I have written. Correct? Any question with respect to proving the first part? Let me just drag it here so that you can copy it. So any problem in proving the first part of this result? So it is 0 when your p is not a multiple of 3. Okay, now let's look into the second part. When p is a multiple of 3, what will happen? So for that, we don't have to rely on this approach. We can directly go here. So if p is a multiple of 3, let's say p is of the nature 3k. That is, let's say p is of the nature 3k. Then what will happen? This will anyways become a 1. Omega to the power 3k. What is omega to the power 3k? And omega square to the power 3k. What are these values? They are anyways 1 each. So what will be the result? 3 only. So that is what this result says. Is it fine? This question actually has come in one of the competitive exams, and it had got multiple options correct. Okay. So it was given in the question 0 when p is a multiple of 3, 0 when p is not a multiple of 3, Like that, options were given. So you have to be aware of what happens when P is a multiple of 3 and not a multiple of 3, how the result changes. Is it fine? Any question with property number 4? Okay, let's move on to property number 5, which is actually the location of cube roots of unity. Location of cube roots of unity on the Argand plane. Okay. So we already know the cube roots of unity are 1 and cos 2 pi by 3 plus I sine 2 pi by 3, which we call as omega also, and cos minus 2 pi by 3 plus I sine minus 2 pi by 3, which is your omega square also, isn't it? Okay. So if I have to locate it on the Argand plane, let me make the Argand plane. So 1 is located here. Let's say this is your 1 point, 1 comma 0. Okay. Omega is located. Now see, this is the modulus 1 and argument is 2 pi by 3, right? So omega will be located at an angle of 2 pi by 3 and at a distance of 1. So at a distance of 1 and this angle being 2 pi by 3, this will be your position of omega. Okay. And omega square will be, either you can take the mirror image about real z axis because omega square is the conjugate of omega, or you can follow this particular method, go minus 2 pi by 3 and again at a distance of 1. Okay. This will be the position of omega square. Mind you, omega and omega square will be mirror images about real z axis. Okay. So this is the location of the 3 cube roots of unity. Note it down. 1 is here, omega is here. As a point, you can write omega as minus half comma root 3 by 2. And omega square is here. As a point, it is minus half minus root 3 by 2. Okay. Now, something very, very important. Note it down. First note this down, then I'll tell you something very important. Okay, so what are the important things here? Number 1, if you connect all the cube roots of unity, you get an equilateral triangle. So an equilateral triangle is obtained when the cube roots of unity are connected. Okay. So if you connect them with a triangle, this triangle that you will be getting, this triangle will be an equilateral triangle. Let me make it for you properly. So let me connect them all. Okay. So this triangle will be an equilateral triangle. Okay. Second thing is area of that equilateral triangle. What is the area of this equilateral triangle? Any guesses? See, very simple. Half base into height, right? Half base. What is this base? This base is the distance between -1 comma √3/2 and -1/2 comma -√3/2. So this distance is 2 √3/2. Okay. And height is 1 plus half, which is 3/2. Okay. So please make a note of this. Its area will be 3 √3/4 square units or unit square. Okay. Also note down the centroid, the orthocenter. What is centroid? Centroid is the meeting point of the medians. Orthocenter, meeting point of the altitudes. In center, meeting point of the angle bisectors. Okay, so these are things which you are going to learn anyways in properties of triangle. Are at origin. Okay, are at origin. So orthocenter, centroid, in center, they are all at origin for the triangle. For the triangle. Is it fine? So few questions around this also has been framed in the competitive exams. They will say that if you connect the cube roots of unity, what is the area of the triangle that you get? So you directly know the result now, which is √3, 3 into √3/4. Sometimes they'll ask you this question, where is the centroid of the triangle located, or where is the orthocenter located? They will be located at origin. Okay. No. It is not for any three roots. It is only applicable for the cube roots of unity. If I am finding cube roots of, let's say, any other complex number, let's say 8i, then this will not be applicable. I'm only talking with respect to cube roots of unity. I'm not talking about cube root of any complex number. Yes, Anika is asking a question. What is the what is in center? Yes, in center is the meeting point of the angle bisectors. Let me just show you by a simple diagram here. See, if you connect the angle bisector, if you make an angle bisector of this angle, let me name it as A, and if you do angle bisector of B, and if you do angle bisector of C, so they will all pass through a single point, and that point is called the incenter. Okay. What is orthocenter? That also I'll draw for you. Orthocenter is the meeting point of the altitudes. So if I draw an altitude, altitude means a line from the vertex and perpendicular to the other side. Okay, so these are the altitudes. This is called the orthocenter. Orthocenter is written with H. Okay. And what is a centroid? Centroid, everybody knows. You have already used it in solving problems of class 10th coordinate geometry also. So let me make a blue triangle. Yeah. So it's the meeting point of the medians. What is the median? From the opposite vertex, it bisects the opposite side. Okay. Sure, Advait, I'll explain it to you. This is called the median. These lines are called the medians. Yeah. Now the medians meet at centroid. So G is the centroid of the triangle. H is the orthocenter. And I here is the incenter. Fine, everybody will now remember these. Yeah, so basically what it's trying to say is that this point, the origin, that will act like the in-center, orthocenter, centroid of this triangle. Let me name the triangle ABC. And let me tell you, for an equilateral triangle, anyways, the in-center, orthocenter, and centroid are at the very same point, right? So even if you drop your altitudes, they will meet at the same position. For example, if I drop an altitude on this and altitude on this, they will meet at the same point origin. And they will also be perpendicular. They will also be bisecting the sides also. Are you getting my point? So these lines that you are seeing here, they will also be altitudes as well as they will bisect the opposite sides also. Is this what you wanted to know, Advait, or you wanted to see this point, third point, centroid? Oh, okay. All right. Any questions, any concerns here, anybody? Okay, let's take few questions based on the same. Once again, I think I jumped to the question. Yeah, this is the question which I wanted to take up. Read this question very carefully. The answer to this question is hidden in the way the expression on the left hand side has been written. You have to find X and Y values here. Okay, so in the interest of time, let me take this concept up. Look at this term, 3 by 2 plus I root 3 by 2. Okay. In this, I would like to take minus I root 3 common. Tell me what will I get? If I take minus I root 3 by 2 common, sorry, minus I root 3 common, won't I get a minus half for this term? And for this term, won't I get plus I root 3 by 2? Correct me if I'm wrong. Agreed? What is this expression, by the way? This expression is actually your omega. Remember, our omega was minus half plus I root 3 by 2. Correct? Now, the question setter is actually raising this number to the power of 50. First of all, 50 being an even number, the minus sign becomes inconsequential here. So it is as good as raising this to the power 50. This is as good as saying I to the power 50, 3 to the power 25, and omega to the power 50. Correct? Now, what is I to the power 50? 50 is what kind of a number? 50 is of number 4k plus 2 type. So I to the power 4k plus 2 is always a minus 1, isn't it? So this will be a minus 1. 3 to the power 25 will remain 3 to the power 25. Now, all of you please pay attention. Omega to the power 50 can be written as omega to the power 48 into omega square. Now, why did I write it as omega to the power 48? Because I know this result is going to be a 1, because 48 is a power of 3, isn't it? So it becomes minus 1, 3 to the power 25 omega square. Omega square is what? Minus half minus I root 3 by 2. So if you pull in this minus inside, it becomes half plus I root 3 by 2. Now compare this result as you can see on the screen here, this result with this result, and tell me who is X and who is Y. Who is playing the role of X? Half. And who is playing the role of Y? Minus root 3 by 2. Don't say plus root 3 by 2, minus root 3 by 2, because there's a minus here also. Okay. So this becomes your answer to this question. Is it fine? Any questions, any concerns? Clear? So basically your omega properties were hidden inside this problem, which we wanted to test. Okay. Now the last concept of this topic that we are going to take up is your nth roots of unity. So just like cube roots of unity, this is a more generalized version where we are going to find out the nth roots of unity. That means 1 raised to the power of 1 by n. Okay. Of course, how many answers will I get? How many answers will I get? Yes, you are going to get n answers from it. Okay, we'll find it out. We will find it out what are those n answers going to be. Okay. So first of all, the same approach that we had taken for cube root of unity. 1 as a complex number, I can write it as 1 cos 0 plus I sin 0. Okay. Let's raise it to the power of 1 by n. That means, by the way, even before that, the step which I normally perform, replace 0 with 2k pi plus 0. Okay. Now, when you're raising it to the power 1 by n, basically you are, by the way, there's no point writing 1 to the power 1 by n. That is actually a 1 only. Okay, but still I'm writing it for your personal satisfaction. So this is as good as this. Okay, so this is 1 cos, or you can remove that 1 also. So this is cos 2k pi by n, I sin 2k pi by n, and your n will take, your k will take values from 0 all the way till n minus 1, right? Not n minus 1, because from 0 to n minus 1, there will be n roots that will be taken care of. Okay. So when I start mentioning these values, the first value will be when I put 0, which is cos 0 plus I sin 0. Okay. That's 1 itself. Second value will be when you put 1, you'll get cos 2 pi by n, I sin 2 pi by n. Okay. Normally some books will call it as alpha. Okay. Cos 4 pi by n. Oh, sorry. While writing n, my writing pad slipped. Yeah. So Next value will be, when you put 2 here, it will become cos 4 pi by n plus I sin 4 pi by n. Now, mind you, my dear, if this is alpha, what would be this called? If this guy is called alpha, what should be the name of this guy? Any guesses? Right, alpha square, because this is just the square of that. Okay. Right, and similarly, the next root will be, I'm just writing few more so that you get an idea. 6 pi by n plus I sin 6 pi by n. Okay. Now, if this is alpha, what should this guy be called? Alpha cubed, right? Absolutely. Okay. So now going to the last one directly, you will be having 2 times n minus 1 pi by n plus I sin 2n minus 1 pi by n. Okay. And as you can rightly predict here, this is actually called alpha to the, this is actually alpha to the power n minus 1. Is it fine? Any questions? Any questions? Any concerns? Okay. Now you will all do a small favor. You'll do a small favor here. The properties which we are going to write down, you are going to take them as a question. Okay. And few of them you will be solving it right now. Few of them you'll be taking it for homework because the time is not that much with us. Okay. So first property is, if alpha is a, let me write it like this. If 1 alpha, by the way, the question setters, they will not be, so kind-hearted that they would write it like this. Sometimes they will write it like this. They'll say, if 1, alpha 1, alpha 2, alpha 3, they will just, put the names alpha 1, alpha 2, alpha 3 like this to the cube roots. To the nth roots. Okay. So that time you have to understand that they are not only, the roots, but they are also these powers of each other. In fact, you can say that they are in a geometric progression. How many of you have heard of geometric progression? Yeah, some of you have, right? So this is actually a geometric progression. Okay. So if these are your nth roots of unity, then please note down that if you add them all, you will always get a 0 as the answer. You'll always get a 0 as the answer. Okay. Now, how do I prove this? Now, for proving this, I need to know the geometric progression sum, which I think many of you are not aware as of now. Okay, not to worry. So GP, geometric progression sum formula, I'm going to give you here. So if you have a geometric progression like this, AR square, AR cube, till AR to the power n minus 1. Here A is the first term. And R is the common ratio. Then this series sum is given by A 1 minus R to the power n by 1 minus R. Now, don't worry about the proof. We'll prove this in our sequences series chapter. Or you can also write it like this. Same expression, nothing different. Both are actually the same things, just written in different ways. Okay. Now, in order to prove this, I'll be using this result of mine. So I'll use the result here. So if I write this series, so using the above result, can I say 1 alpha square all the way till alpha to the power n minus 1. Please note A is 1. Okay. I'm using the first expression 1 minus. Now, common ratio is alpha. N is the number of terms. Number of terms is n itself, divided by 1 minus alpha. Now remember here, alpha to the power n, since alpha is a cube root of unity, is going to be 1, right? Since alpha is a nth root of unity, alpha to the power n is 1. So this is going to be 1 minus 1. And by the way, 1 minus alpha is, I mean, if you want, I can write it as 2 pi by n. Okay. So this is going to be a non-zero term, and numerator will become a 0. Okay. Alpha is not 1, by the way. Alpha, if alpha is 1, then it would be already written over here. Alpha is, this 1 is separate here, right? 1 is also a root, not denying it. But alpha and 1 are different. They're not the same. This is my alpha. This one, which I put a tick mark. This is my alpha. 1 is separate root. Okay. So this is how we end up getting the value of 0. Clear? This result should be kept in mind because this result will be utilized in solving few questions. Is it done? Can we move on to the next property? Should I go on to the next property? Okay. Nobody is responding means everybody is copied. Property number 2. The previous property, in fact, I should say an extension of the previous property. If I start raising all the nth roots of unity by a power of p, okay, like this, then note down this result will be a 0 if p is not a multiple of n. Now, are you able to connect this property with the omega thing that we had done? In fact, omega, 1 omega and omega squared, they are special cases of this, where your n value is 3. Sorry, I wrote a 3 by mistake. It's n. Yeah. Okay. And what should be the answer if p is a multiple of n? Can you take a guess? Absolutely right. The answer should be n. Correct? Now prove this for homework. I'm not going to do it right now. Prove it for your homework. Same thing, you have to just apply your GP formula here also. Nothing different. Nothing different. Okay. Property number 2. This was an extension of 1, so I'm not putting a separate name to it. So I'm just calling it as extension of property number 1. Okay. Property number 2 is 1 minus alpha, 1 minus alpha square, and so on and so forth till your last 1 minus alpha to the power n minus 1. This value is n. Now, this is a question which is worth solving. Okay. How many of you here know a bit of limits? How many of you here know a bit of limits? I know I have not done it with you, but just wanted to check how many of you know. You just started in school. Okay, how many of you do not know limits at all? Okay, some of you are saying barely, some of you are saying Nothing at all. Okay. All right. So it will be slightly challenging for me, but I'll try my best. Okay. If you use limits, you'll be solving it in a faster way. Now, let us start with the fact that nth roots of unity, let's say I call that as a complex number z, right? What does it mean? It means z to the power n is 1, which means this will have roots 1, alpha, alpha square, and so on. These will be the roots of this equation, correct? So this is an n degree polynomial equation. So this will have n roots, and those will be your 1, alpha, alpha square, etc. That means z to the power n minus 1 can be factorized as, or let me say this expression has z minus 1, z minus alpha square, etc. as factors. So these are the factors of this expression. Can I say that? That is to say, z to the power n minus 1 can be written as z minus 1, z minus alpha square, and so on to z minus alpha to the power n minus 1. Yes or no? Yes or no? Can I write it like this? Everybody is happy so far. Okay. Now, if that is the case, you will all admit that I can write z minus 1, z minus alpha square, and so on to z minus alpha n minus 1 as z to the power n minus 1 by z minus 1. Can I write it like this? So I've just brought this term to the left side. So it goes below the z to the power n minus 1 term, right? So it comes as a denominator to that. Any questions here? Any concerns so far? Okay. Now, if I ask you a simple question, does it look like a sum of a geometric progression? If no, then you will be able to identify it now. Does it look like a sum of a geometric progression? You'll say yes, and that geometric progression is 1 z square, and so on till z to the power n minus 1. Correct? Yes or no? So finally, what we have got? Finally, we have got this expression with us. Okay. Now here what I'll do, since I want to get this expression, see here, since I want to get this expression, can you tell me what z value should I substitute here to get that? What z value should I substitute here to get that? Oh, sorry, this is not going to be starting from 1. This one has already gone down, right? It has gone down here. So this will not be it. Yeah. So what will you put z value as? 1. Correct? So if you put z value as 1, what will be the left hand side becoming? 1 minus alpha square, 1 minus alpha cube, and so on till 1 minus alpha to the power n minus 1. Right side will become 1 plus 1 plus 1. How many such ones will be there? N such ones will be there, right? So this will be your n. That's your right hand side, hence proved. Clear? Any questions, any concerns? This has come in the JEE main exam. This question, this property itself has come in the JEE main exam. Now, later on when you study limits, I'll be telling you one more way to evaluate it by taking a limiting case of z tending to 1, but that is for future. As of now, you have not learned limits at all. So that's the reason I solved it in a different way. Note it down. Okay, so with this, I will leave you with a homework on the very same concept. Try out this question. Prove that, again, 1 alpha, alpha square, etc. They are nth roots of unity. Okay. So if these are nth roots of unity, then prove that 1 plus alpha, 1 plus alpha square, 1 plus alpha cube, and so on, the product till 1 plus alpha to the power n minus 1. This value is 0 if n is odd. Okay. Sorry, 0 when n is even. My bad. And 1 if n is odd. Okay. Do this for homework. The approach is very much similar to what you have done right now. Okay. Try it out. We will discuss it in the next class if you have not got it. So with this, we end this topic of complex numbers.